the camera. Tuesday, the 25th, March 25th, homework quiz on chapter 22. And Thursday, the 27th, the master set for chapter 22. Any questions? Okay. We last left off. We derived the speed of an electromagnetic wave, found out that C is equal to 1 over the square root of the permeability of free space times the permittivity of free space. That would be the speed of an electromagnetic wave through a vacuum. From this, talked about the debate in physics of whether there was a mistake or not. And if there's no mistake here, then this means the speed of light is constant regardless of reference frame. For example, if I asked, how fast are you moving? Well, let me ask you, how fast are you moving right now? Not necessarily a trick question.
Not really at all.
Okay. Anyone else with a different answer?
Must account the rotation of the Earth.
Oh. Should we account the rotation of the Earth?
I don't know the reference frame for the questions.
And that's the point of the fact that there's nothing in that equation that has anything to do with how fast, of what reference frame. So, if this is to be believed, if there is no reference frame, this means that the speed of an electromagnetic wave, or let's just go ahead and say speed of light, is the same regardless of how fast you're moving. And if that's true, then time is not the same for everyone. Because up until this point, it was believed that time was the constant and not the speed of light. All right, that was the last thing that we did. So now we're going to drop back from that and talk about solid state. Homework quiz on chapter 22, week from today, week from Thursday, master set for chapter 22.
Okay.
And that's a recap for the review. Student introduced this memory trick to me a couple years ago, and I liked it. So I'm just going to present that for right now, and then we'll come back to what this means later. we've talked about DC circuits. Let's talk about an AC circuit. So first off, if I have, so AC, alternating current. As opposed to DC, direct current. If you have, so DC is what we dealt with till now. So in a direct current circuit, the drift of the electrons is always in the same direction. In alternating current, it's oscillating back and forth. We are, the US and Canada, probably Mexico, are on alternating current. Europe is primarily on direct current. Now, the big advantage of alternating current, especially when the standard need to be established in this country, is alternating current loses less energy over long distances. Whereas in Europe, they don't have the huge open spaces that we have in the US. And so we definitely need something like this. There's a big debate. This was supported by Westinghouse. This was supported by Edison, who was famous by then. And so Edison tried to do whatever he could to make this look bad. So when it came to doing, well, basically, he wanted alternating current to be used for the electric chair and the death penalty because he wanted people to associate alternating current with death. Ultimately, this went out. So let's get into some of the more specifics. The symbol for direct current, as we've done so often, that's the symbol for a direct current power supply, I should say. A DC power supply. The AC power supply, indicating the fact that there's not a positive and negative side, or at least that the positive and negative side flip back and forth. That's the symbol. Now, if it's also, if you'll, for those who've had some trig, you might notice that kind of looks like a sine wave or a cosine wave, whichever way you want to go. And so in alternating current, the voltage of alternating current generally is symbolized by some amplitude, E sub n for max, times either cosine or sine of omega t plus phi. This is the angular frequency, as we mentioned, I think 2 classes ago. This is the phase shift. Time, amplitude. Now, for whatever reason, when we get into the notation, you typically stop using the delta V. Instead of using delta V, you use epsilon to represent the EMF, which is the ideal. So typically I'm not going to write it like that, but write it like that. This is just using, it basically came down to, we're dealing with the EMF, which is an ideal voltage. What Greek letter starts with E, epsilon, we'll use epsilon. Just to add to the confusion, when textbooks were being written, however many years ago, obviously no word processing, the thing was being done by somebody putting letters in. Not everyone had the epsilon. They had capital E, which it kind of looks like. So you will see, especially in electrical engineering, they'll use capital E to represent epsilon, which represents the voltage. This is not E as in energy, this is E as in EMF. So this E right here represents the voltage. I'm going to take a basic AC circuit. And I'm going to stick a resistor into it. I can still do voltage gains and losses, so I'm going to start here and I'm going to go around. So I'm going to gain some potential here, I'm going to lose potential there. And when I say gain potential, since this is oscillating back and forth, my gain might be negative. So I have my EMF from the power supply, and then minus IR would be equal to 0. We did something incredibly similar when dealing with DC circuits, and if there were a DC circuit, then it would be delta V is equal to minus IR equals 0. If you'll notice, not only do we have the epsilon versus the delta V, we have a lowercase I versus an uppercase I. Lowercase I represents the formula for the oscillating current, because the current's going to be moving back and forth also. Voltage flips back and forth, current flips back and forth. So if epsilon is equal to epsilon maximum cosine omega t plus phi minus IR equals 0, we can now solve for the current. I equals, bring that over, epsilon, so max over R cosine omega t plus phi. Dramatic pause for people to catch up in writing and to ask questions. Because my wife doesn't know I'm here. I used that line a couple of years ago. Who was always taking a picture. I said, "Don't put me in it. My wife doesn't know where I'm here." And she said, Where does your wife think you are?" I said, "With my mistress." That person was not necessarily the best audience for that. All right, so we got some major things coming out of this. I mean, it just looks simple, not a whole lot of highfalutin math here. But this maximum voltage over the resistance is my maximum current. This is just the amplitude of current. So I can also write this as capital I, or capital I now represents the maximum current, cosine omega t plus phi. So we have that the maximum current is equal to the maximum voltage over the resistance. We also have, if I plotted this, let's just assume that the phase shift is 0. In other words, my cosine curve is going to start at its maximum, and then that's basically the cosine. This is time axis. This is my EMF, and this would be 2 pi over omega, and it would keep on going. That is my graph of my EMF, the graph of my resistance, now I drew it smaller. Without knowing what R is, I have no idea whether, I mean, they're on two different scales. Same time scale, but different vertical axes. So if you drew the green line larger than the black line, that's fine. But notice that they peak at the same places, they bottom out at the same places, they cross zero at the same places, they are completely in sync. Or, as physicists would say, they're in phase. So for an AC circuit, current and try that one again. EMF and current are in for a resistor. Now, again, might not seem like much, but it will become more important later. Questions? And we also have epsilon sub max. So I've got my voltage there, or we can do voltage, or there's a mistake over here. That green line is current for the resistor. It should be, the green should be current, not resistance. Now I'm going to take my AC circuit and I'm going to put a capacitor into it. Again, I have some EMF going across my power supply. It is oscillating back and forth. We're still going to, let's keep the same value right there, or the same equation, minus the voltage across the capacitor is equal to 0. What is capacitance anyway? Capacitance. The basic definition. Formula. Basic formula.
Basic formula for capacitance is the magnitude of the charge over delta V.
Yep, that's the one I'm looking for. So if I know the voltage across it, I can figure out what the charge is. So just manipulating this slightly, we end up with delta V is equal to Q over C. So I can figure out what the potential difference is across a capacitor if I know the charge and the capacitance. So my equation here becomes the EMF is equal to Q over C. But I really want to know what the current is. What is the relationship between current and charge?
A current is the charge over, my brain remembers it. I equals the charge over, time?
So charge,
The number of charges over time, or just charge over time? Change
Uh,
in charge over time. Change
J.
over time. There we go.
it's generally written
Sorry.
as change in charge over time. That's supposed to be a lowercase q there. Let's try that one again. It's how much charge passes by a certain point at a particular time. So we have this current is equal to delta Q over delta T. I'm using the lowercase q here because again, we're talking about the charge on the plates is changing. It's not a, there is a maximum amount, but it's the same notion as my current using lowercase I for alternating current, lowercase q for the alternating charge on the plates. So I have now, I'll multiply both sides by C, so I have C epsilon sub epsilon is equal to Q. Actually, that Q right there, sorry about the notation mix-ups here. That should also be a lowercase q. Lowercase q, lowercase q. If I plug